Okay, so is it visible? Screen is visible, or should we close this light? Okay. So now there is a gap, so we need to recover what we were looking at. We were looking at RSA crypto system, and especially I have to tell you how an attack, uh, what are the attack strategy on RSA crypto system. And as you know, that RSA crypto system is based on integer factorization, right? So given an integer, if you can point the large primes P and Q such that P into Q is equal to N, so then we can actually mount an attack. That I will show you how we can mount an attack if we know P and Q. So the question is, now given an integer, first of all, how do we check that it is a prime? So this problem is known as primality testing. It's a very old problem, goes back to the Gauss and other people who tried to discover a polynomial time algorithm for finding, uh, you know, prime number for an integer to check whether it is a prime or not. Now, as I mentioned, so Neeraj Kayal, Nitin Saxena, and Manjur Agrawal found this in 2002, 6 August 2002 actually. They reported this algorithm, which is polynomial time algorithm for finding whether an integer is prime or not. Before that, there were several interesting development. I think I told you about Las Vegas algorithm, right? What is Las Vegas algorithm? That what is Las Vegas algorithm? Anyone? It will give you an answer. Huh? Sometime it may not give you an answer, right? So that is a possible, right? And there is another set of randomized algorithm known as uh, Monte Carlo algorithm. So Monte Carlo algorithm actually they may give a wrong answer also. So that is a important thing. But if you run in them enough number of times, actually the probability of error could be minimized. Okay. So the goal is if you construct an algorithm, a randomized algorithm from primality testing, you need to check, you know, that number m, how many times should I run it so that we get, with probability of error to be low. So we call it probable prime, so that number is known as probable prime. So there are two popular algorithms. Of course, there are many other development I'm not going to touch, otherwise there will be whole class on primality testing only. But I'm going to look at two algorithms, maybe one I'll see which one. So, that is, I'll show you how that algorithm works. So before that, I think as I have already done this calculation for you about uh, quadratic residues calculations and the Legendre symbol, right? So you know what are the formulas, how do we compute it? Obviously, one can look at the complexity of these things, how difficult it is to compute these things. So let me start with these two algorithms. So a Las Vegas algorithm may not give an answer, but any answer it gives is correct. Whereas Monte Carlo algorithm always gives an answer, but the answer may be incorrect. Okay, so that is a key difference. So there are two randomized polynomial time algorithm, Monte Carlo algorithm. First one is uh, SS algorithm, we call it. Another one is Miller-Robin algorithm, right? So these algorithms are fast, but they may claim that n is prime when it is not. So that is a key thing, you know. So they may give you a wrong answer, which is a important thing to observe. Okay. So basically, one question that comes into mind: how many random integers we need to, we need to be tested until we find the one that is prime. So Gauss actually, while looking at the tables of prime numbers, actually he guessed this formula that the pi n is number of primes less than or equal to n. N is a fixed integer. How many primes are there? Less than n. So we know that there is no compact and closed formula, but at least this asymptotic formula is there, that this number behaves as n by log n. It's known as prime number theorem, very famous number theoretic result. Okay, so if a number p is chosen at random between 1 and n, probability that it is prime is about 1 by log n. Okay, so now if you are looking at in our RSA crypto system, if n is of 2048 bit, okay, that modulus is, then p and q are primes of 1024 bits basically. So in that case, a random 1024 bit integer will be prime with probability about 1 over 710. So that means on average, given 710 random 1024 bit integer p, one of them will be prime. Okay, so this is a rough calculation in terms of where our RSA crypto system stands. Okay, so now there is a decision problem, which is known as a problem. So a question is to be answered either yes or no. So these are kind of problems which are known as decision problem, right? So which is very common thing. So there is something called as yes bias Monte Carlo algorithm and no bias Monte Carlo algorithm. So yes bias Monte Carlo algorithm, it's a randomized algorithm for a decision problem, yes. So answer is always correct, but a no answer may be incorrect. Okay. So more biasness toward yes. Okay. So yes bias Monte Carlo algorithm. Okay. Then there is a no bias. Similarly, you can talk about no bias Monte Carlo algorithm, right? Which has more biasness toward no. So a yes biased Monte Carlo algorithm has error probability epsilon. If for any instance in which the answer is yes, the algorithm will give the correct answer no with probability less than epsilon. Okay, so that is a probabilistic remark actually. So again, I'm just recalling that Loss Vegas algorithm may not give an answer. Okay. Uh, but any answer it gives is a correct. Whereas Monte Carlo algorithm gives an answer, but the answer may be incorrect. Okay. Okay, so there is a decision problem, composites, right? A positive integer n greater equal to whether it is composite or not. That's a question that you can ask. Yes, it is composite. No, it is not composite. Those kind of decision problems are popular problems studied. Okay, so now I think we are ready to give you this algorithm, SS algorithm. Stetson has done a lot of work actually on complexity of, in fact, in terms of matrices, there are a couple of algorithms from his, in terms of numbers, arithmetic, he has given a couple of algorithms, especially multiplication. Some very good algorithms are given by him, right? Okay. So, uh, so this algorithm is a yes bias Monte Carlo algorithm for composites with error probability half. Okay. So now there are certain results which I think if n is greater than 1 and an odd integer. Okay. So we know that n is prime. If n is prime, then Legendre symbol a by n is congruent to a raised power minus 1 by 2 mod n for any a. And this 0 if and only if the GCD of a and n is greater than 1. Okay. So these facts actually, and if a is between 1 and n minus 1 and this Legendre symbol is 0, then n may be, must be composite actually. Okay. So these are the results which are useful. Here is the algorithm. Choose a random integer a between 1 and n minus 1 and then compute this symbol a by n and we assign it to x. If this turns out to be 0, then return that n is composite. Okay. And also compute this a raised to power n minus 1 by 2 mod n. If x is equal to y, congruent to y mod n, then return that n is prime, else return that n is composite. So this is a very simple algorithm. Basically, essentially, we are just using the fact that I mentioned to you. So the question is, what is the complexity? So there must be some complexity for actually computing. So for computing this symbol, actually there should be a complexity. So let me tell you roughly how much is the complexity that people have computed. So there are two arithmetic operations in a by n, modular reduction, and then factoring out power of 2. Okay, so the whole thing is less than big O of log n. So in fact, it's very interesting thing to actually look at, that total complexity is order of log of n whole cube. Okay, for computing only this portion, for computing only this portion. Okay, so I think this we have already done. This can be further reduced to order of log n square. So I'm not doing any of those calculations right now, but I need to mention it anyway. Now, actually, I'm going to ask, I want to compute this probability. Suppose we have generated a random number n, okay, and tested it for probability testing using this SS algorithm. If we have run the algorithm m times, so if we have run the algorithm m times, what is our confidence that n is prime? Okay, because we know that this is a Monte Carlo algorithm. We need to run it certain number of times and to make sure. So how we can compute this probability? So probability that such an integer n is prime is 1 minus 2 raised to power minus m. Okay, so let me actually define some random variables. So suppose a is the random odd integer n of a specific size is composite. This is your random variable a, and b is the algorithm answers that n is prime m times in succession. Okay, these are two random variables. So one can see that this probability of B condition A is less than or equal to 2 raised to power minus m, and we have, so I want to compute probability of A condition B. In order to do that, I should know that what is the probability of A. Okay, so first of all, I would like to find out this probability, and then I can use Bayes' theorem, if you know, to compute this probability. Okay, so let me do that calculation for you. Suppose n is a integer between capital N and 2n. Using prime number theorem, so number of primes, odd primes of course, between n and 2n is approximately 2n divided by log 2n from prime number theorem. Okay. So this is something around, n by log n is equivalent to so basically, I can compute that probability of A turns out to be 1 minus 2 of log n. Therefore, probability of A condition B will be probability of B condition A times probability of A divided by probability of B. Using Bayes theorem, right? So I can compute these things. Okay, so we are somewhere around, I am just skipping a couple of steps. So we will be having probability of B condition A 1 minus 2 of log n divided by probability of B condition A times 1 minus 2 of log n plus 2 by log n, and the whole thing again using this, that probability of B by A is less than or equal to 2 raised to power minus m, and so on. We will arrive at 2 raised to power minus m log of n minus 2, 2 raised to power minus m log of n minus 2 plus 2, which simplifies to log of n minus 2 divided by log of n minus 2 plus 2 raised to power m plus 1. All these calculations I am skipping, but anyway, I think I might be having a table here. I am not sure. So I think with these calculations, I can with certain numerical values, I can say that if m is equal to 50 or 100, so that will reduce the probability of error for this algorithm actually. So of course I have skipped a couple of steps here, but I hope that's okay actually, so you can look at it. The next algorithm is the Miller-Rabin algorithm. So here we, n minus 1, we write down as 2 raised to power k times m, if m is odd. Consider a random integer a between 1 and n minus 1. Then compute a raised to power m and name it to b. If this turns out to be congruent to 1 mod n, then n is prime. For I is equal to 0 to k minus 1, we run this loop. If b is congruent to minus 1 mod n, then return n is prime. Else we compute b square and put it in b modulo n, and then return that n is composite. So this is a Miller-Rabin algorithm. I think and I can just say that the complexity of this algorithm is also order of log of n whole cube. So this algorithm for composite is a yes bias Monte Carlo algorithm. I think this much is enough, I guess, for you to. Let me now actually do some little bit more calculations. Keep it here. Now attack on RSA. So we know that Euler torsion function phi of n is there. So from n I can find out phi n, right? So suppose we know n and phi n, then we can actually, how do we find these primes? So we know that if n is, because here n is product of two prime numbers p and q. So phi of n, because p and q are prime, so their GCD is 1, is p minus 1 into q minus 1, right? Then I can find out n minus phi n plus 1, and this turns out to be p plus q. So that means p and q are roots of the equation x square minus n minus phi n plus 1 times x plus n. Well, this is the product of the roots, and this is the sum, that basic formula, right? This can be written as x minus p into x minus q, right? So essentially, if n is given and phi of n is given, and if you can factor this, right, then I can find what is p and q, right? So this is a very basic way how we can attack, right? So that is the whole thing. Anyway, so I think that's all for today. Probably I will just do a couple of these things later on, especially the last algorithm. Okay, so one thing I hope so many of you, I have seen there are about 75 submissions right now in the project, right? So there are about 32 students who are giving exam right now. I mean, at the present data, I'm not sure. But some of the presentations are very poor actually. PPTs are very poor. So either I'll give you feedback or you modify or whatever, it's up to you, or you want to, should I grade it like that, or if you want an improvement, then I can tell you what are the issues, okay, so that you can improve it, okay. So I think that's what we can do probably in a day or two, because I think today also many people are not there, right? They'll come on 13th, right? Most likely. So we will do few things maybe in the next class, okay. So I think now you can start working on the project, and see if you can do something meaningful by the end of the day, okay. Thanks, and I think that's all for this. uh, yeah, so I think after that we have, already we are doing, I think, chapter 6. So after this, these are some algorithms on attack on RSA. Then after that, we are going to look at elliptical crypto system, which is very, very important. And then probably this time we can do a little bit more as compared to the last time, because we just briefly gave you one lecture on this. And then, but remember now, these things are more mathematical, right? Whatever cryptography you see is a different thing, as because this is what is the real thing. Okay, it's all algorithms at the end of the day, right? And the complexity. Okay, so we'll talk about these things later on.
submit થાય કે વાળો ફોર્મ ફિલ